Digital World Town Hall meeting on today, April 9th, 2024. We're grateful for you taking the time. We're grateful for those that are also co-hosts, as well as any kind of administration that folks may be doing here. This is a private membership association. Some of the things we may talk about might be forward-looking. Today, we're actually joined by a special guest, Samuel M. Smith, who created not just Carrie, but many other things in his life. He's a wonderful man based out of Utah, and he's primarily focused on not just reputation, but a lot of things that benefit humanity. And we've worked with him for many years, but grateful for the days that our paths crossed and we get an opportunity to kind of go through and understand his history as it relates to technology and innovation and really humanity, and how he's been forging the way from a development standpoint, and not just the technology, but architecture as well. So grateful for him taking the time to join us here. Um, he actually graduated in not just engineering, but computer electrical design. He's done some crazy things with submarines and some artificial intelligence before artificial intelligence was actually a cool thing. And I'll let him kind of tell the story there. But before we do so, I want to help you to understand some of the specifics that he has really been influential in. And there's a long list of things that he is.
World 4/9/2024.
Margaret, you got to mute, dear. Welcome, welcome. It's good to hear your voice, though. You're okay. So he's built many things, not just some of the things we'll talk about today, but anything around decentralized ID. I believe that a majority of it came from what he's been building and innovating on, even before what they call the Sovereign Foundation was created. So grateful for him taking the time, and grateful for those others that are also on this call. I'd like to just kind of give you an overview of the specifics of what we actually adopted, which is actually key event receipt infrastructure design by Samuel M. Smith. And it goes through a lot of elements around how you can actually verify an individual. We called it the Maria Gonzalez problem. At least one angle of it was a Maria Gonzalez problem, where there were 24 little baby girls born in Orange Hospital, California on the same day, and their parents gave them the same name. So how do you know and understand how those individuals can actually verify or be identified through life? Well, they'll say, well, maybe a social security number, or maybe this, or maybe that. And really, ultimately, the issue is deeper than that. So a lot of the things that Sam is actually focused on help solve that, along with that particular problem came from a gentleman named Richard Dick. And there's also another key engineer that worked on this. His name is Conrad Rosenbach. So these are some of the folks that actually help with one of the original technologies that we kind of worked on together, which was called the Universal Genealogical System. So a lot of the technology and innovation comes from genealogy, believe it or not. And so this was kind of a baseline, as well as Roy Curtin, as well as David Loper. These are wonderful people that helped to build some of this innovation and technology, but there are a lot of it around ID was directly built on what Sam Smith actually created. So the details go long, but this is a universal genealogical standard that was basically created before anything around the digital world, anything around the reputation. So again, it's important for you to understand the man behind a lot of the technology and just be able to hear from him, what drives him, why is he doing it, why is it important, who's adopting it, who is actually targeting it or testing it for future. I think all of these are very important points. And so with that being said, Sam, lead us in any direction that you want to take us that you think is important for our listeners to hear.
Okay, great. So I'm trying to think of the best place to start.
Maybe start with some of the crazy stuff that you did with artificial intelligence before the world even cared about it.
Yeah, so I got my PhD from BYU in 1991, and so I was working on AI in the late 80s. Back, and some people think AI is a new thing, but what people were calling AI or machine learning or automated reasoning got started as soon as there were computers. So in the 60s, people were saying, "Oh, we could do artificial intelligence with computers." Back then, computers were pretty. Even a supercomputer was much less powerful than the cell phone in your pocket by orders of magnitude. But the basic algorithms of machine learning were invented back in the 60s, 70s, and 80s. The only thing that has really fundamentally changed since then is computers have gotten more powerful. So the same algorithms can be trained on bigger data sets so they can start to approximate human class behavior, because now the data sets are comparable to the data set that a human is trained on. And when you think about it, a little baby is trained on terabytes of data in just the first year of their life, because everything they see with their eyes, everything they hear with their ears, everything they feel, touch, or do is training data. And so you know, and the brain of an infant is still, you know, the numbers are huge, times more powerful than the most powerful, you know, network of supercomputers. So AI has been, you know, an exercise in waiting for Moore's law to build more powerful computers to get more capability. But there's still certain fundamental things that humans can do that no supercomputer or no projected one, at least, you know, pre-quantum computer can even hope to do. And there are other things that we know that humans can do that machines can't do. But so back in the late 80s, we were trying to solve some hard problems with different types of learning, because neural network, they called them multi-layered perceptrons back then, and you could only do like three layers, maybe 5 layers if you're lucky, you know, just weren't very good learners. And now we have deep learning neural networks, but they quickly run into their performance limitations. So now we've developed reinforcement learning and self-supervising learning and large language models, which look under the hood like stuff that we did back in the 80s. We just didn't have, you know, petabyte data sets to train them on, which is why large language models actually work, is because of the size of the training set and different ways of training. So one of the things that I realized a few years ago when I got into the identity space is that I was trying to solve the problem of the broken internet. And so this is back in 2014, 2015. And back then, if you remember, social networks had taken off, and the behavior of people online was just horrible. And you know, it didn't matter where you went, you know, trolls could come in, say bad stuff, people would leave comments. And you know, it's even worse now, but back then it seemed like, wow, this has gotten really bad. How do we fix that? And so started looking at the problem of, could we build AIs that would act as an assistant to help filter the data that you saw by giving you an algorithm that said there's certain people that you want to talk to and certain people that want to talk to you, and you don't want somebody else telling you who they are. So right now, when you go onto a platform like YouTube or Facebook, their own AI is telling you who you can talk to, and they're suggesting videos that you can see or other people to talk to you, and it's their proprietary algorithm. You don't control what those parameters are, right? And a lot of what they send you is guided by stuff that will make them money, by advertisers, right? And so the advertisers are basically saying, well, based on this person's behavior, we want to put stuff in front of this person because we believe their behavior indicates that they're somebody we want to sell to. And that's not what we want. We want to control who we talk to, who we see, and what information we see on the internet. That means we need to own our own AI. We need to own our own algorithms for deciding who we can talk to. In order to do that, you have to own your own identity on the internet. You have to own your own data. You have to be in control of how that works. And right now, and back then, this was 8-9 years ago, you don't own anything on the internet. You're under the control of whoever controls your identifiers and your identity. So if you log in with Facebook Facebook controls everything. It's their identifier. It's their account. They can kick you off at any time, and they own all of your data. And the same thing with every other large social media platform. So the challenge was, how do we build identity systems that are owned by the people themselves? And that gave rise to something we call self-sovereign identity. The problem in the early days, we didn't know how to secure those identities, so we put them on blockchains, which is a good first step. The problem is blockchains have increasingly started to look like platforms in their own right. So your identity's locked to a given blockchain. It's not portable across every infrastructure. So a few years ago, I spent time trying to figure out how to remove the blockchain. We call it ledger lock. And the thing is, when you have identities owned by blockchains, then you get the ledger wars, because every application that wants to use decentralized identity has to make a choice. Which ledger do we base everything on, right? And so everybody that has a ledger competes and says, no, you want to, pick me. And what happens is that no adoption happens because there's just too many ledgers. So it took a while, but I came up with a protocol called Carry that allows you to not be locked to a ledger, to have security better than on a ledger, be portable, and be totally decentralized and owned by each entity that wants to create an identifier. So that's the big picture. And I'll stop there for if there's some questions, or I have a slide deck I can start to go through to sort of explain some of the details under the hood about some of the features. There's 150-page white paper.
I'm actually scrolling through
numerous other documents. We're now on a standards track for ISO. We're starting to get some significant adoption of some of this technology.
I'm actually scrolling through the white paper as we're speaking and just kind of listening.
Yeah. Well, can I share my screen on this?
Yeah, go for it. Yeah, no, go for it. It's all you.
Okay, I'm not familiar with this app as much. So where's the controls for sharing? Oh, there it is.
Down below, there's a button with an arrow that's going to the right. So that's
okay. Yeah, that's probably this one.
That work okay for you?
Michael, we're getting so much background noise from you. It must be the wind or something.
Yeah, somebody's got wind blowing. I don't know who that is.
I'm sure it's Michael.
I'll pop off on this one.
Here, it looks like it's not letting me share that window, so I'm gonna close some other windows. Just share this screen. I think this will work. Okay, see if that works. Okay. So let's see if I can share my screen. Try again. I'm not sure. Are you seeing anything? No, it's not sharing. I don't know. We got. Oh, there we go. They'll have to be on. Maybe it's the Windows. I'm not sure it likes multiple monitor setups.
There you go. It's doing something now. It just shared and then went away, Sam. It just shared and then went away, Sam.
Yeah, I don't think it's not letting me share my window. So
okay, no worries. It did share, but we'll go ahead and. I saw your screen.
I'm just not seeing it share on my end. So
okay, no worries.
All right. Well, we'll just not try to share then. My setup might be complicated for it.
You did
so
share.
Maybe I can just talk to a couple of things then.
You did share your screen for a second there. I don't know if you knew that, but it was sharing for a second.
It did share it for a second?
Yeah, it did. want, I've got some good illustrations and things that we can run through. I don't know if you were seeing my screen or not, but I think we've done a really good job in some cases to simplify the user's experience.
Which window is it showing? Is it sharing a window?
No, nothing right now. So that's okay.
Okay.
That's all
Let me
right.
try sharing the screen.
We'll give it another 30 seconds and then I can just share some of the elements that I've got. There's parts and pieces that.
Yeah, I'm not. It's bringing up this window, but I'm not seeing how it's letting me pick a window to share. So that's what I'm confused about.
No worries, no worries. It might be the first time that you're into this tech, so
Yeah, I haven't ever used this sharing app before, so
it's okay.
I'm not familiar with how
Well,
it works.
there you go. There you go. You just shared it right now. You're sharing it. No?
Oh, okay. It's got a. Oh, I see what it's got. It's got a thing in the. It's got a little control up at the top. No, it's just sharing. I'm trying to do a presentation. It's just sharing the same window that I'm on, not a presentation. So
No worries, no worries. I'll go ahead and just share mine.
Yeah.
So to speak. So,
sorry about that.
no worries, no problem at all. So I'm now streaming your image, and what I'll do is I'll just walk through with folks. I've got the. I don't know if you can see my screen share here, but I've got your white paper up, and
Oh, okay.
just kinda
Yeah,
walking through that.
actually a better one would be bring up one of the slide decks. So if you go, since you're navigating into GitHub, yeah. Oh, you're in there. Yeah. Just go to. Yeah, you see it. Yeah, carry. You see a carry overview. Is there a carry simple in there? Probably not. Yeah, just do the carry overview. Then that's fine. Or actually, there's a carry for muggles. That's probably a good one on that last one that you're at.
ACDC for muggles or carry?
Carry for muggles. Carry for muggles is.
Got it.
Where is the carry for muggles?
I've got it.
There we go. Right there. There we go. Okay. So we'll do this one. If you could just advance the slide deck.
No problem.
So this is sort of like a carried me simple. So just go to the next slide. The key of carry, the key idea is that, and it stopped sharing for some reason, is that we want to have people need to control their identifiers. So if you think of an identity online, an online identity, the only way anybody knows who you are is by your identifier. That's the thing that you can use online to send emails, to send texts. Certainly can show your, the picture of yourself, but since anybody can fake pictures and stuff like that, the picture doesn't necessarily mean that it's you. So you need something that doesn't ever change, or more importantly, something that you can uniquely prove control over, so that you can out of band means not using the internet or using part of the internet that somebody can't predict so they can't attack it. Prove control over an identifier, and then anytime you use that identifier later, people know that it's you. And so that identifier has to survive forever. It has to be an unbounded term identifier. And you can choose not to use it, you can abandon it, but the identifier itself has no lifetime or limit. It persists indefinitely. So the old way of looking at identifiers was that you had public and private keys, and the public key was the identifier. The problem is that the public key and the private key, when you use them, become weak. And so you need some way to change them without changing the identifier.
Let's
So
explain
if you
to
go
folks,
to the next slide.
let's explain to folks why they become weak. It's like a credit card. You use it over and over and then it just leaks out, right?
Yeah. So if you pay attention to all the hacks that are happening of companies every day, multiple companies, somebody's attacked them and compromised something, and it's usually because some secret that they're using gets exposed. And so if your private key is being used in your computer, or you're using it, in something to do something with it, over time, because you use it, an attacker might be able to discover it, and it's called a side channel attack. Or you might be careless with it, and you might accidentally let it leak out, right? So the fact that things can leak, and maybe it takes a long time. It might take.
Let's give an example of that. So, like, people use credit cards, and they have a public 16-digit number that's on the front and a private 3 or 4 numbers that are on the back. That's a good example of why banks need to say, hey, every 4 years, you're going to get a new credit card, whether you want it or not. And it's just, they give you, the credit card system is just broken. You give out your public key and your private key every time you go and buy a soda pop at the store, Go ahead, Garrett. Go ahead.
Well, yeah, every time you go to a restaurant and you give your card to the waiter or waitress to go do your payment, they now have both the public and private key. And I've had to replace half a dozen credit cards that, the day after I used it at a restaurant, I started getting charges on it. So I knew that somebody at that restaurant photographed both sides of the card and then started using it, because they could call up, they could log into Amazon, and Amazon says, give me your CVV code. And they go, here's the CVV code, and so they can start buying stuff.
It just doesn't make sense how humanity just continues to let this be. I mean, it's just mind blowing to me. And it's still, even to this day, it's a normal thing,
Yeah. The thing about the internet is that it's been broken from the beginning. It's just that we've gotten used to working with a broken system. So if it doesn't break every time we use it, we say, well, I guess that's okay.
Well,
but
maybe
from a security perspective, if it breaks even a little bit, or only every once in a 1,000 times, that's one too many, because the consequences can be huge.
Have you ever asked yourself, maybe it's by design that it's just not secure? Whether it's the payment systems or the
it's
internet?
not secure because in the early days, people didn't believe that that people could manage their private keys, and so they had to let somebody else manage them for them. And so we have federated identity.
Okay.
And federated identity now gives those people control over your identity. So they have a vested interest in going down that path. And it's an easy tell to people to say, hey, we can't expect you to manage your identifiers. Don't we'll manage them for you. Right. So there's lots of ways to do it. So the first thing that Carrie is based on is something called a self-certifying identifier. And a public-private key pair, the public key and a public-private key pair, is a self-certifying identifier. And that's what the basis of PKI started with is, hey, we invented this great thing in cryptography called public-private keys, and you can take the public key and use it to prove something. The problem is that you have to rotate those public keys. So what we want to generate an identifier that's derived from the public key. It isn't the public key, but it's derived from the public key. And so you derive it with a cryptographic process. So you have this other identifier that's a cryptographic identifier derived from the public key, and you can prove that it's derived, and only the person that holds the public key can prove that they own that identifier. And you can create any number of identifiers that way because they're cryptographic looking identifiers, so there's no collisions. You don't have to do name squatting, right? I mean, the identifiers aren't user friendly, but we can make the user interface is user friendly without making the identifiers user friendly. So that's a false dilemma to say, well, we can't use cryptographic identifiers because they're not user friendly. That's a false dilemma. We can use them under the hood and make it so that people don't have to see them. So this is the process that makes it self-certifying. You have a controller, that's an individual legal entity. They capture entropy, that means random numbers. They generate a key pair. They then derive from that key pair an identifier and other information, and it's a cryptographic derivation. And now anybody can challenge them, and they can verify that they control the identifier, because they can provide the derivation algorithm and the key generation algorithm, and only the person that controls the private key can prove control over both of those. So we can go to the next slide. So that means that you can prove control of an identifier without needing to rely on anyone outside of your control, even a blockchain. You are totally in control of that identifier, and nobody can create that same identifier and prove control over it because of the entropy that you capture. You capture enough entropy that in a million billion years, no one could ever guess the same private key, so they can never generate the same identifier because there's just too many of them. So it's impossibly small probabilities for somebody to be able to do that. So now you can control your identifiers, right? Now the next step is, how do we make it so that I can change my public and private keys under the hood without changing the identifier? We do that with another self-certifying thing called a self-certifying key event log. And so a key event log is what we call a verifiable data structure. Now, I'm going to confuse you for just a second, because everybody uses the term blockchain, and unfortunately, it's a simple word that is used for something that isn't a blockchain. So when you use Ethereum, people call Ethereum a blockchain. People call Bitcoin a blockchain. They are shared distributed consensus ledgers. Now, it just so happens that shared distributed consensus ledgers happen to use a data structure called a blockchain, right? So the ledger under the hood is a blockchain. What is a blockchain? It's called a hash-chained data structure. It's a cryptographically verifiable data structure that's chained together with cryptographic digests or hashes, and some of them are signed, right? But what makes it a shared ledger is the fact that that you have an algorithm, a distributed consensus algorithm. Well, in Carry, we can use the verifiable data structure, so if you can scroll back up, without needing the shared distributed consensus ledger. And so that's what makes it portable, is that we're going to use a blockchain, but that blockchain there is a blockchain for each and every identifier. They get their own. So it's totally portable. You can erase it, so you can be forgotten, and anybody can verify it, and only one person can control it. So only one person can write to it. And they can verify that they're the right person writing to it, because every entry has to be signed by the keys that control the identifier to which the blockchain belongs. And what is in this ledger, this blockchain? It's your key state. It's the state of the keys that control it. So it's sort of like you're pulling yourself up by your bootstraps. So you have these messages, and these messages change the key state. And each message is signed, and each message is linked to the message before it, forming a blockchain. So after you create it and you share it with somebody, you can't change it. It's immutable. They verify it. And so it gives you all of the capabilities that using a blockchain gives you, but without all of the complexity and the governance and the cost and the latency and stuff like that, because it's just a simple data structure. So what it does is that you change your keys by putting events, creating events. The events say, hey, I'm changing my keys. Anybody can verify that you change those events. And now they know what your new keys are. And so when you want to rotate keys, that's what rotation is. You revoke your old keys, you replace them with new keys, And now you have new keys and you start fresh, but the identifier doesn't change. And the key event log is actually locked to the derivation process of the identifier. So when you do the derivation for your identifier, you're also including the first event in your blockchain in that derivation. So nobody can get ahead of you. You're always one step ahead of an attacker.
So another simple way to say it is your credit card, instead of having to have it replaced whenever you think somebody's gotten it or when the bank just replaces it for you, you basically automatically can replace it, but there's no centralized bank that has been tracking your ledger or chain. So it's ledgerless, but you can still validate who you are, and you never have to get a new credit card. Is that a good way to put it?
Yeah. I mean, there's no shared ledger, right? It does have a key event log, which is a type of ledger, but it's not shared. Nobody else controls it. You control it.
Yep. And
you can always prove your key state by sharing, by giving out your ledger, but it's not held in, somebody doesn't own it. You control it.
What a concept.
So we don't call it a ledger because it's too confusing. We call it a log. It's just a key event log. It's just a log of events, but under the hood, it's a block. It's a type of blockchain, but it's not a shared distributed consensus one. So I don't even like to use the word because people have in their mind what they think it is, and it's technically not accurate. So I just say it's a key event log.
Most of the folks,
and you can have witnesses that you control that sign copies of it, so that you can have high availability. People can see if your witnesses are consistent. If somebody attacks your witnesses, they'd have to attack the majority of them. So it gives you the ability to add security and availability to your key event log.
I'm on slide 22 now. So this is a use case example.
So a witness is like anytime you do something and you sign something, you can have a notary public sign, and that lends reputation, credibility to whatever it is that you sign. So your witnesses are things you control that can sign as well. And now an attacker has to attack not just you, but all of your witnesses.
Yep.
And that makes it really secure.
That's a good way to put it.
And then you go to the next slide. Yeah. So here's what a key event log looks like. So the controller has a key event log. Each witness has a key event log that they sign and they receipt. So that's where the receipt comes from in Carry. Key event receipt infrastructure is that you create events, and then witnesses generate receipts for the events. And now any verifier has to see all of those to verify it. And so it makes it really difficult to attack. And so we can go to go to the next one, 24. So I think I already said that. All right, keep going. Number 4. Okay, now we're going to talk about the magic of Carry. And it's called pre-rotation. And this is what allows you to recover control, not even when your signing keys have been compromised. So let's say they've leaked out and they've been compromised. Well, if I'm using a traditional blockchain, if my keys that control my address on the blockchain are compromised, now whoever compromised them can then put transactions on the blockchain and take control of whatever assets or whatever I have there, because the blockchain itself says, well, whoever signs the transaction, they must be the owner. And if and it doesn't have a way to do key rotation. If you want to rotate your keys, you have to create a new account, move all of your stuff to the new account with the new keys and do a transaction. And you have to do that on a regular basis to protect yourself from key compromise. But with Carry, you have something called pre-rotation that allows you to recover control even if your keys are compromised. Now, we're not talking about assets with Carry. We're talking about control over an identifier, the reputation associated with the identifier, proving that you are in control of it. And so you might lose control temporarily, but then you recover, and everybody can reconcile that you recovered, and they can see which events were bad events and which ones weren't, and then you're back in business. So the idea is that you actually create two private keys, the signing key and a pre-rotated key. The pre-rotated key you don't use, so you don't expose it. In fact, you could bury in your backyard or in the bottom of a coal mine, protected by a bunch of Navy SEALs. never sees the light of day, it's air gapped, all of the most secure measures, and the attacker over the internet can't attack it because it's not anywhere that they can get to. But you make a cryptographic commitment to that key when you create your key event log that says, in order to rotate my current signing key, you have to use this key that I'm not disclosing, but I can make a commitment to. So you can take the digest of the key, and the digest is unique. They don't know what the key is. They can't invert the digest. But when you use that key, they can prove that it was the one and only key that you used, that you designated. And it's a very simple thing that we call it pre-rotation, because you commit to a key, you create two keys, commit to one, you use the other, and if the one that you use gets compromised, then you do a rotation event that can only be signed with the pre-rotated key. And so the attacker can't ever rotate, even if they compromise your keys, your signing keys, they can't gain control of your identifier because they can't do a rotation event. They can sign things, but they can't put an event that says, oh, here I controlled the identifier, I rotated. They can't do a rotation event. So pre-rotation protects your rotation events from the normal types of attacks. So this is sort of an example. You go inside your bank wallet while you're private, you generate key pairs for future use. You go to the next one. You sign proof of the next public key. You put that proof in the signature on your key event log, but you never use that key. And then later, when you need to do a rotation, then you go wherever you protected that key, you can take it out, use it to do a rotation event, and recover control over your identifier, even though your signing key has been compromised, because your signing key can never be used for rotation. Only your pre-rotated key can be used for it. So you go to the next slide. So this simple, so in the event that something's compromised, right, you just go back and get that other key and use it, and you use it before an attacker can get to it. And you can use it once. It's only once. You can only use it once as a pre-rotated key. And so when you do a rotation, you create the next pre-rotated key. So every time you do it, you're one step ahead of an attacker. So you just stay one step ahead forever, indefinitely. So you don't need anything more sophisticated than that. And so this simple thing called pre-rotation is really the magic that makes carry possible to be ultra secure, use everywhere, be portable, do whatever you want, because it gives you a way to manage your keys in a secure way. Simply, it's not complicated.
Let's go ahead and just pause here for a second. Let anybody ask questions. I've got some limited time on the system, so to speak. But anybody have any thoughts or questions or feedback, or I can kind of show you how we've actually implemented some of this brilliance. Go ahead and just give you guys a second here. I'll show you while you're thinking. So this is the digital world, and you basically have three different reputation systems that are built into it. One is around the individual, one is around the organization, and one is around the asset. And they all follow the same key rotation as derived keys off of the private master key pair that basically Sam is talking about. And the simple way to be able to make it so that humans can actually use this. So on the left, you have an individual that says, I'm willing to use data that comes from me that can only be from me. It's not from a machine or some type of system that can validate or try and copy me as an individual. And on the right, people can say, well, I care about that data or not. So it builds trust with just two simple screens in a world where reputation can actually be starting to be validated. Now, we believe that this has a long ways to go before, well, maybe talk a little bit about some of the adoption that you've currently seen as far as what systems, organizations, standards, bodies have actually adopted this type of technology.
Yeah, there's an organization called the Trust Over IP Foundation, and you could just look up TOIP Foundation if you want to take them there. Trust Over IP. Yeah. There you go. trustoverip.org. It is a member of the Linux Foundation, which includes the Hyperledger Foundation, some other foundations. And there you see Carrie. So we have a suite of standards that we're right now in public review for 3 different standards, about 200 pages total of standards documents that we're then going to go from the Trust for IP to the Linux Foundation, and then from the Linux Foundation to ISO. ISO is the international standards body for standards worldwide. And so hopefully by the end of 2024, this Carrie suite of stuff will be an international standard so that everybody can use it, open source. And once everybody can use it, then the tooling, the applications, the adoption can expand so that everybody everywhere in the world, not just people, but organizations of all types, can own their own identifiers, their own identity, and everybody else can verify it. And so it will change how the world works over the internet. Because right now, the internet works on what's called federated identity. And that means your identity is owned by some identity provider, whether it's Okta or Google or Amazon or Facebook or LinkedIn or whoever it is, right? They own your identity. You get a username and a password, and they give you permission to use their site. And often they give you free stuff to use it, but they own everything you do on that site. It's not yours. But with Carrie, you own your identifiers, which means you can own everything else that's associated with those identifiers, but it will take time to get there. One of the places that it's being adopted is there's a organization set up by the G20. So we're talking, the G20, those are the 20 largest countries in the world. After the 2008 financial crisis, realized that one of the reasons that the financial crisis happened is because of fraud in the financial industry. They didn't know who was who or who owned who. They didn't know that, for example, a given bank was self-insuring because they all had different names and they were hiding things like that. So if a bank went bankrupt, its insurance company went bankrupt, and then every bank that insurance company was insuring went bankrupt, and then their insurance companies went bankrupt, and then the banks that were insuring went bankrupt, and it quickly cascaded into a global failure. So the G20 said, we need a way to identify, things on a global basis, all right? And so they created something called the verifiable legal entity, the legal entity identifier, which became an ISO standard. And a few years ago, in 2020, GLIFE, the Global Legal Entity Identifier Foundation, set up by the G20, wanted to make their identifier cryptographically verifiable. So they started doing it in 2017. They spent several years and millions of dollars trying to figure out a way to do that. They thought that they could do it on the blockchain, but they ran into the